Assalamualaikum and salam sejahtera. Welcome to section 2.6, Controllability and Observability. Okay, in the previous section, we learned how to determine stability of a system by using state space method. And in this section, I will continue to explain another two important terms in control system, which are called controllability and observability. I will also discuss on how to identify controllability and observability of a system by using state space method. Let us start this section with controllability first. Okay, actually, in the field of control system, it is important for control engineers to have ability to control the system. Actually, the term control means the engineer must have ability to control all the state of the system, and this can be achieved actually by changing the input of the system. Or in a proper definition, a linear system is with state vector x is called controllable if and only if the system states can be changed by changing the system input u. Controllability of a control system is important to ensure the control engineers able to design a control system for a given dynamic system to meet their objective. So the question is how to determine the controllability of the system. Okay, a system is completely controllable, or all state variables are controllable if and only if its controllability matrix MC defined by B, AB, A square B until A n minus 1B has a full rank of n, where n is the number of state variables. If the rank of MC is equal to the number of state variables, it means that all the input are connected to the state and therefore the system is controllable. However, if the rank of MC is less than the number of state variables n, it means that some of the input are not connected with the states and therefore make the system uncontrollable. Okay, we can also identify the controllability of the system by calculating the determinant of MC. So, for a system to be controllable, the determinant of MC is not equal to 0. However, if the determinant of MC is equal to 0, it means that the system is uncontrollable. Okay, in this example, we will try to determine the system controllability for the given state space equation. So basically, to determine the system stability, we only need matrix A and matrix B, and also the number of state variable n. And in this case, the number of n is equal to 3. Okay, now we use matrix A and B to calculate the controllability matrix MC. Okay, since the number of state is equal to 3, n is equal to 3, the MC will become B, AB, A square B. We already has B, so we need to identify matrix AB and A square B. So AB or A times B is equal to 1 minus 1 minus 2. And A square B, or actually A times AB is equal to minus 2, 1, 4. Okay, now we can obtain the MC using the value of B, AB, and A square B. From the controllability matrix MC, we identify its determinant and we get the answer is minus 1. Okay, since the determinant of MC is not equal to 0, then we can simply say that the matrix MC has a full rank of n, or in other words, the number of rank is equal to the number of state variable. So the system is controllable. Okay, next I will explain about observability. So what is observability? In general, observability means that we can observe and measure the system state variable from output of the system. Or specifically, a linear system with state vector x is called observable if and only if the value of the initial state xt0 can be determined from the system output yt that has been observed over a finite interval of time from t0. However, if there is no connection between the state variable and the output of the system, then the system is called unobservable. Observability is important to ensure control engineers able to see what is going inside the system under observation. Okay, to find observability of a system, we need to find the observability matrix M0, where M0 is equal to C, CA, CA squared until CAN minus 1, where n is the number of state variables. If the rank of M0 is equal to the number of state variable, or we call it full rank, then the system is observable. In contrast, if the rank of the M0 is less than the number of state variable, then the system will be unobservable. The observability of the system can also be obtained by analyzing the determinant of M0. If the determinant of M0 is not equal to 0, then the system is observable. But if the determinant of M0 is equal to 0, then the system is unobservable. In this example, I will explain how to determine system observability from a given state space equation. Basically, we only need matrix A and matrix C to determine the system observability. We know that the observability matrix M0 is given by C, CA, CA squared until CAN minus 1. And for the system, the number of n is equal to 3. Therefore, the M0 can be rewritten as M0 equal to C, CA, CA squared. We already have matrix C, so next we need to determine CA and CA squared. Okay, then we substitute matrix C, CA and CA square in this equation to obtain M0. And from the matrix M0, we further identify the determinant of matrix M0. Okay, since M0 is equal to negative 344, which is not 0, we can see that the M0 has a full rank of n, or the number of rank is equal to the number of state variable, and therefore the system is observable.